Fortunately, it's brilliantly written software. I mean, Robert's worked on some of the software, and he can attest to that, right?
Yeah, I'm pretty sure that physicists can write code, but they don't like to write code.
So who wrote it? Or is it physicists originally, or do you hire like software engineers?
Both. We hire undergraduates who are in, one of the fun things about working in particle physics is if you like electrical engineering problems, we have them. If you like mechanical engineering problems, we have them. This detector weighs 17,000 tons, and you're trying to understand where all the pieces are to microns. Okay, there are 1,200-ton pieces that are. No, I'm getting the numbers wrong. I'm actually getting the numbers wrong here. But they're kiloton pieces that were lowered 100 meters underground in the frame.
Very carefully.
Very, very carefully, with only a few centimeters clearance on either side. And then there's online software. There's a whole online software challenge. There's offline software. You might see periodically announcements about world records set for data transfer between North America and Europe. Yeah, that's particle physicists setting those records because there's so much data to push around. They've been figuring out how you push data on the net faster than anybody else can.
And this shows you also after the control room where we have the PCs and the monitors connected to control every piece of the detector. And every sub-detector has its own place with lots of monitors.
12 screens there. That's just looking at the power state of the detector, whether it's on or off. Which is ridiculous, but that's what they do. And there's about 4 times as many, well, maybe even more than that, 5, 6 times as many screens sitting there in that room.
Excellent question.
I was going to say, so at the end of the day, how many people who have a PhD, let's say, are working on this? And if it's a huge success, who gets the credit?
Everybody.
We all co-author the papers.
So we have about 2,500 PhDs right now.
How do you write a paper? How does that appear on the paper?
Well, I can tell you, it takes a while. So usually what happens at some point, we just went through this process for the first time, looking at data that was taken last fall with the detector from cosmic rays, basically. We're 100 meters underground, but we still see about 100 cosmic rays coming every second through the detector. So people analyze that data to see if the detectors are working. We wrote papers in the winter, and I don't know, you have a period where the people who've worked on that part of the analysis write down the paper, and it gets reviewed by your colleagues, and then everybody in the collaboration can read the paper and send comments. It's all web-based, and we got about 80 pages of comments for a 10-page paper from much less than the 2,500 people. So then you spend 2 weeks looking at all the comments. Some of them are duplicate, and hopefully they agree that you solved their problems for them, and then we publish a paper. So the first physics paper will be more than 80 pages of comments, I guarantee that.
Because everybody will read it.
Everybody will read it. People will say, and you'll get comments that say, you didn't give too much information here. You should tell us more how you did. Section 3 is not complete. Somebody else will say, Section 3 is way too long, and you gave too much detail. So then you have an editor who says, what the policies are. So the more senior people in the collaboration, people who've written many papers and maybe even review articles for journals, or even our editors of journals are involved now on our collaboration. So by the time we send a publication out to be published, it's already been reviewed by 2 or 3, times the number of people who will see it in the journal process. So, but it's quite different than a small group writing a paper, right? If you have 5 people in your group, the first author might mean something. And on particle physics papers, the first author is the guy who has the most A's at the beginning of his last name, or woman.
And the experiments are so big, odds are you have somebody with multiple A's.
The Danish guys usually win that battle.
All true then.
Yeah. So
are your groups here at Rice going to be transitioning to data analysis projects? And so have you already picked which ones they're going to be?
Well,
So I know they're
the real reason why they're here this week, in part, was for us to ask them, so what's your physics analysis going to be? And we're still discussing it. So it's still a bit far away, and they've been working hard, and we're all working hard on understanding the detector at the moment. There's a phenomenal amount of detail that's going on, trying to understand the detector and the detector response, to try and get the best information. But we've been, at Rice, our group has been preoccupied with that. So we're still discussing.
So once you have the data here, I imagine it's not it's not going to fit on like a terabyte drive or whatever. So how do you manage the fire of the news?
Yeah. Anyone? Somebody else.
For the data transfer,
Yeah.
we have, right now we have already data, but if you think about physics analysis,
Speak up.
data. Okay, so far we have already data at Rice, and we analyze offline study using Rice computers and data, and it works really fast. But for physics analysis, I think we need big cluster for that, and we have a grid to use, so we have.
Yes, you've heard of the grid.
You heard about the grid.
So the data actually is spread out all over the world, and so Rice is.
We're a node on the grid.
We're a node on the grid, and we can go to our desktop or your laptop, and you log in, and basically on a website you're authenticated, and you can find out where the interesting data that you want to run on is. Some of it might be in Italy, it might be in Chicago, it might be at CERN,
nowhere.
it might be in Russia, wherever, and you send your job out, so to speak. It's like a giant batch system, but it's distributed over the web, and then you have to collect your data back somehow. And I think we were just talking today in a meeting about an analysis that another postdoc who's not here, who's at CERN, is working on. It's about 10 or 20 gigabytes of data now. This is the final reduced amount from what might be a few months of running for one analysis. And the raw data is we write how many terabytes a day? I don't remember.
It's terabytes a day.
Terabytes a day. And so it gets shrunk down, and the part you're interested in is this little tiny, 1/1,000,000th or 1/1,000,000,000th of the data. It gets shrunk down at every stage of the analysis. So a lot of it happens at CERN. Some of it then goes, tier 0, and then, which is where they do the first reconstruction. Then that's distributed around the world to about 7 different places, and they reduce it more. And eventually it comes to your laptop. Your laptop might be called a tier 4. So tier 3 would be like our computer center here at Rice.
And it's very unlikely that you lose important stuff when you're cutting it down.
No, that's one of the important things you have to make sure you're not doing.
So you don't want to do that. Right.
So the actual getting the physics result out is almost the easiest step.
Yeah.
And it's all the cross checks to make sure you haven't done something like that
Yeah.
that take all the time. Especially when you don't know what the signal is that you're looking for. It gets tricky. Coming back to the original question, the guidelines from computer people who have done estimates of the data and the physics volumes is that a typical grad student analysis will be on a data set that's boiled down to 1 or 2 terabytes. Okay, so you skim through the data and pick off and presumably get down to 1 or 2 terabytes, and that's something we can cope with here.
Yeah.
And we're sort of set up to do that. And so, a grad student's PhD analysis should be something that we can sit at a decent desktop and do here after it's being filtered down sufficiently to the last steps.
And I should say the network stuff is great, but if you want to sit there and make a lot of plots and see things changing, you want to do it on a machine you're sitting right in front of. You don't want to send those graphics over the web. X Windows is the worst, but there's some other tricks, but they still it's nothing like seeing it in front of your eyes, right? I mean, graphics cards are so fast; they're much faster than network. So you had to share that network with everyone at Rice. That's not good.